When we analyze a circuit and we want to analyze a varying value over time, let's say voltage, we take that value, that varying value, and we put it on a Cartesian plane where the x-axis represents the time and the y-axis represents the amplitude. And this is what an oscilloscope does, sweeping a luminous dot across the screen. So in this video we will see the fundamental components of an oscilloscope, its basic usage, the differences between analog versus digital oscilloscope, and a final intro to some advanced operations. And the tips and tricks here and there, so be sure not to skip any part of this video. These are the fundamental parts of on oscilloscope, the fundamental blocks, and this is specific of the analog oscilloscope, and I start with the analog oscilloscope because it is better to understand basics. So we see here this part that is the sweep control, and it is formed by the time-based generator and the ramp generator. The time-based generator essentially determines the times that the ramp generator takes to complete the sweep, and this controls the x-axis so that the dot draw a line across the screen on the axis on the x-axis, and here we have the intensity and focus, the screen controls. And in digital oscilloscopes, we may have further controls such as the opacity of the graticule. And here the trigger has the function to detect a level at which point the time generator is started, synchronizing the sweep to that specific level. And the trigger can be set to work with an external signal or with the internal signal coming from the input of the x-axis. And here we have the signal conditioner that is composed with by one attenuator and an amplifier. And its output controls the vertical motion of the dot along the y-axis. Now you would wonder, what is this trigger and why there is one? All waveforms are typically periodic. It means that they repeat themselves over and over again. So when you want to display them on the screen, you have to decide at which point to start to draw the line, to draw the waveform on the screen. And that is where the trigger comes. It is the level at which point we want to start the sweep that draw the line of the waveform on the oscilloscope. So let's see where the relative controls are located here on the front panel of the instrument. So here we have this, that is the time-based control that with this knob that allows to select various time, sweep time. We have the trigger section here, and here we have this part that is specific of this instrument, that is a hybrid oscilloscope with a memory. Here this LED indicates that we are triggering the signal, and then here we see this part that is the amplifier and attenuator of the X channel 1 and the X channel 2 inputs. Here we have another attenuator because this is a two-trace oscilloscope, and here we have the control that allows us to select which channel we want to see on the screen, and or if we want to see both channels. And here below we have the controls for the screen, the intensity and the focus. At the input we have the Y positioning control, the phase inversion, the coupling switch that have the G and D position, useful to place the trace at 0, and the AC coupling, useful to read the AC component only in the case of an AC signal. is overlapped to a DC component and the DC coupling position that provides the true signal. Finally, the attenuator allows to select the proper amplitude and its adjustable knob for a finer control. Here we can switch the two channels, so now we are seeing the second channel. The square and pseudo-triangular waveforms both come from a test circuit made around a 555 IC, so they are synchronous. We can also see both waveforms contemporarily with the dual command, and in this case the channel selector has the purpose to route the selected channel's signal to the trigger. When using dual or more traces on analog oscilloscopes, we have a special control that inserts a chopper that chops the signals into slices that are alternatively displayed on screen. This is useful when looking at low frequencies or with long time base. Without this function, the instrument alternates the traces at each sweep, and we choose this last option when we look at high frequencies or with the short time bases. And we can also add the signals from the two channels by pressing the add button, and we can also make the subtraction by inverting the phase of one of the two channels. And this is the time base control that allows us to have a view of more periods or less periods, zooming into the waveform. And around here we have the controls for the trigger. Here we have the automatic and normal operation. We will see better later on. And here the button to allows the external trigger, and here the level of the trigger, and here the button that allows to select the trigger on the rising edge or the falling edge. And here a filter that allows us to detect to pick the trigger level from the DC or the AC of the signal, and exclude high frequency, exclude low frequencies, and to synchronize to line or the mains voltage frequency. For example, here in our test circuit I've simulated a for condition where the power supply presents a strong AC component. The signals are heavily affected by this superimposed AC, and triggering on either channel while holding stable the square and the triangle waves, it is unable to hold the superimposed frequency, which therefore is uncorrelated. Switching to line mode trigger, suddenly we notice that the superimposed waveform stops from scrolling while the other waveforms scroll. This is a clear sign that the superimposed waveform is correlated with the mains frequency, and in a real situation this could be a hint to spot the origin of the anomaly. Now let's understand the normal and automatic trigger mode of operation. In normal mode, if I don't have any signal, you see nothing on the screen, but as soon as I have a signal, I see the signal on the screen, and this is the normal operation. And it is quite hard when you have no idea of the signal you are looking for, so it is better to start with the automatic operation, because in that case, even if the signal is missing, you still see a line on the screen, so you can adjust the position or have an idea that what's going on. Even if the signal is not synchronized at all, you can still see something on the screen. But as soon as you have a stable signal, you can switch to normal operation to have more precision with the trigger level. As you can see, as I move the level of the trigger, the waveform is shifted because I changed the level at which point the trigger starts to synchronize the waveform. As you can see here, is at this point at the minimum level, and moving this changes the point, increasing the level and moving to the top of the waveform. When we reach this point, the synchronization is lost again because the trigger is not able anymore to find the point, and this indicator light is turned off. As you can see here, is still visible again. As I go below this point, the indicator light turn off, and the waveform is not longer displayed because the oscilloscope, the trigger is unable to find a point of start of the waveform. Now, before starting operations with the oscilloscope, it's important to adjust the calibration of the probes. This protruding grommet is an output specifically designed for this purpose. The probe needs to be set for calibration as specified, typically switching to attenuation if it is in a dual 1:1 and 1:10 attenuated probe, and set the input for DC and adjust the amplitude to cover the full upper screen. Also set the time base to display some cycles. Then with a special screwdriver provided with the probe, adjust this leader screw. As you can see here, I demonstrate two different improper calibrations, while the proper adjustment when we see a neat square wave. It might take a while. It is important to remember that this calibration is meaningful only on attenuated probes, attenuated by 10 or by 100 or more, and because there is no compensation on probes that are not attenuated. You may wonder why using attenuated probes. There are two reasons. One is to limit the voltage if it is beyond the capabilities of the instrument. And the second reason is to minimize alterations to the circuit under test, since an attenuated probe has a higher impedance. Keep in mind that the attenuator scale should be scaled with the added attenuation of the probe. So, for example, with a 10:1 probe, this settings becomes 2 volt per division. And this brings us to how to read the waveform on the screen. The screen has an overlapped graticle, and the graticle provides divisions on the y-axis and the x-axis. And so on the y-axis, each division equals to the selected attenuated voltage per division. So, for example, in the voltage we have set right now was 2 volt per division. So here we have 2 volts, and so this waveform reaches a positive peak, which is right about this is 1.4 volt, because it reaches this point, and the negative peak reaches negative 2 volts. And this is on the y-axis, while on the x-axis we have 0.5 milliseconds per division, or 500 microseconds per division. So between this point and this point, let's align a little bit better, we have 1 milliseconds, little bit less than 1.5 milliseconds, and the full cycle is about from here to here, which is 1, 2, 3, and 4. So it's 2 milliseconds and 2.1 approximately, 2.1 milliseconds. So the frequency will be 1/time 476.2 Hertz. We've seen that the trigger offers different various facilities to adjust the level of the trigger, but also it has a filter and a coupler which allows us to couple on AC, DC, high frequency or low frequency. So a trick here is that in many cases for smooth waveforms like this one, it works better using the DC coupling of the signal, because it allows us to adjust the precise point of the waveform we are interested in. When we read waveform like this that have a long section of the waveform that is stable, like a DC voltage, we have a range of adjustment that, as you can see, doesn't change anything. So in this case, it is better to switch to AC, so we directly detect the peaks of the change, so we can simply neglect to adjust the level, because this assures us that the peak is detected, so we can synchronize to the age of the waveform, and we can change the polarity of the age that is detected to change the synchronization position from here to here, or from here to here, which is the same thing. The high-pass and low-pass filters can come handy to filter out spurious signals from the trigger detector. So, for example, to filter out high-frequency spikes, the low-pass filter helps avoiding to synchronize to such spikes. One important point to remember is that instruments have limits. So one limit here is the bandwidth of the instrument, of the amplifiers, that limits the maximum frequency that can be shown on the display. And the other limit is the voltage, the limit of the amplifier and the attenuator, and the maximum voltage that the instrument can hold. Beyond that, the instrument is not longer able to hold that voltage. So it is important to keep in mind these limits and use proper probes for the purpose. So the first step to do when we want to measure a circuit is to have a rough idea of what we want to see on that circuit, what we want to analyze, what are the voltages that are intended on that circuit. But what if we don't have any idea of the voltage we have to measure? Well, first, of course, we have a very rough idea of the voltage, because that is a hard limit of the instrument. And then we can start with some adjustment to make the correct measurement. So when you have no idea of what you are going to measure, the default adjustments should be to put the time division to a pretty low frequency, but not too low, and set the trigger to automatic, and reduce the and increases the attenuation to maximum attenuation, so you are sure that the voltage that reaches the instrument is attenuated enough. Sometimes you can get lost. There is no signal here. No, it was just too high, too faster the time base. And what's going on here? Well, it's the attenuator that is too low. And sometimes you change the frequency, you change the trigger. It seems that it's triggering even at normal, even at automatic, but you see nothing. Put this to GND, and voila, the trace was off the screen. So adjust the position of the trace, and the signal appears here. On a digital oscilloscope, the only part that is similar to the analog oscilloscope is the attenuator and the amplifier. Then it is followed by a sampler, something in hold circuit that stores the data on the memory, and a clock, internal clock, that moves the memory locations for each sample, and then again we have a trigger and a time base that are relatively similar to the analog version, and the time base now control the memory scan, and this is of course an approximation of the real thing, and then the output is displayed on the screen. The sampler and hold and memory are among the most critical components in a digital oscilloscope, as they determine the speed at which the instrument can grab the input values. It is radically different in respect to an analog instrument. The word that the instrument allows you to know is limited inside the quantization. Everything is outside it is ignored. This means you may miss a sample where an actual event happened. While on analog instruments you are limited to the bandwidth and the speed of the phosphor decay, here you are limited by the quantization time and resolution. An analog oscilloscope is a tool to exploit physics to display the instantaneous amount of electric charges on a continuous line of events. A digital oscilloscope is an abstraction. And here we are seeing the same waveform that we've seen on the analog oscilloscope. Here we have the digital oscilloscope, and in this case on screen we have a lot of information that make our life easier. And important information that is different from the analog oscilloscope is here, which is the sample rate. Interesting feature is that moving the trigger lever, we can see not only the voltage of the lever, but here we can have a feeling of the lever that is projected on top of the waveform. Another advanced feature is that we can stop the instrument from grabbing samples, expand the view, and scroll not only after the triggered event but also before. For example, we are here at 6.2 milliseconds before the event. This is because the instrument has a continuous circular memory, and the trigger happens at the middle of this memory size. The indication is the time position. On certain instruments, this is indicated as delay. Therefore, negative numbers refer to the history before the trigger and not after, as in this case. Another characteristic typical of digital oscilloscopes is that visualization of the waveform can be interpolated using vectors or using dots, or displaying just the dots that represent each sample. And here you can see each dot represents one sample, so you can understand that in the middle, between one dot and the other dot, we don't know nothing of what happened in between of these points. And this is just joining the dots, where there's a lot more to say about oscilloscopes, and in particular to the digital oscilloscope, but that goes beyond the scope of this presentation, that I hope you enjoyed, and if so, please hit the thumb up icon and subscribe to the channel, ringing the bell icon as well. For now, that's all, folks. Thanks for watching. See you next time. Bye.